All right, hi, and welcome to the, Earth, Ocean, Geo, and Atmospheric Science Mini Symposium. I'd like to introduce Artash as our first speaker, and let me just remind everyone in the session that the talks are 25 minutes, then we have 5 minutes for questions, and then we will have subsequently 5 minutes for transition after that. If you have questions, it's best to put them in the Q&A. So that we can find them later. And with that, I think I'll hand it over to Artash.
Thank you. I'm going to go ahead and share my screen. All right, here we go. Hey everyone, good afternoon. I'm Artash. I'm a grade 9 going into grade 10 student from Toronto, Canada. And for the past 5-6 years, I've worked on several projects related to space, science, geoscience, robotics, big data, and today I'm going to be talking about one of my projects on using seismic vibrations to measure the effectiveness of COVID-19 lockdowns. So let's get right into it. So COVID-19 first emerged in China in December 2019, and it quickly spread to countries around the world. On 11th March 2020, the World Health Organization declared COVID-19 a global pandemic, and this had a cascading effect as countries around the world closed national borders and enforced lockdowns to stop transmission of the COVID-19 virus. Canada was no different. 2 weeks after the World Health Organization's announcement, all Canadian provinces and territories had enforced some form of lockdown, whether that's closing non-essential businesses, cutting down on non-essential travel, closing some of the public areas, and even my school was turned online. Now, these lockdowns are absolutely essential to stop human-to-human transmission of the COVID-19 virus, but they have a huge economic, social, political, and mental health costs to our society. So they're only effective if citizens actually comply with the lockdown restrictions. So I wanted to find a way to understand whether the lockdown legislations are working at keeping people at home and reducing human movement in cities. This would allow politicians to take rapid decisions and enforce surgical lockdowns based on time and location. So to measure the surface level changes in human activity, I ended up turning subsurface to seismic vibrations. Seismic vibrations are measured through seismic stations. Seismic stations are usually used to measure natural ground vibrations, such as one from earthquakes or volcano eruptions. But they're so sensitive to seismic vibrations that they can even record anthropogenic seismic vibrations caused in cities by urban reasons, caused by humans, such as construction, cultural events, sports events, cars on a highway, school buses going to school. So if I was able to extract the seismic vibrations caused by urban reasons from the seismic stations, I would get a good idea of the changes in human movements in the cities. Luckily, the Canadian National Seismograph Network operates a network of over 150 seismic stations across Canada. And all of this data from these stations is aggregated together in an easy way through the Incorporated Research Institute of Seismology. So I had a lot of seismic stations on my hand, but I needed to select which ones I would be using for my study. So I came up with 4 criteria. First, since I was looking to measure the changes in urban noise, the seismic station should be close to a city center, so ideally within 50 kilometers of a city center. Second, the seismic station should be active and recording seismic data from before and during the lockdown period, so I could measure the differences. Third, the data from the seismic station should be transmission live and should be open to the public. And finally, the seismic station I choose for my study should give a good representation of the entire geographical area of Canada. I ended up choosing 9 seismic stations scattered across 6 provinces of the Canadian National Seismograph Network, which were mostly located near big cities. Now, here's the interesting thing. The next part, I needed to extract the human vibrations from the seismic stations. So what's interesting is that while natural ground vibrations, like the ones caused by earthquakes and volcano eruptions, happen at a lower frequency of 0 to 2 hertz, human-caused vibrations, such as from construction, mining, and transportation, happen at a much higher frequency of 5 to 20 hertz. So I wrote algorithms in Python that use specifically the SciPy library to calculate Fourier transformations in the data. So what I did is I broke the data into 15-minute periods with a 50% overlap and calculated the Fourier transformation of each segment. What the Fourier transformation basically does is it gives the intensity of seismic vibration inside my sample over different frequencies. So as shown on the table, the top table where it says intensity of seismic vibration, then you can see a graph. It shows the intensity of different seismic vibrations at different frequencies. So I was able to use Python to extract the seismic vibrations that were specifically within the 5 to 20 hertz range, which are caused by human activity. I then compared these high frequency seismic vibrations from before to during the COVID-19 lockdowns. So some of the other libraries I used was OBS-Python for extracting and downloading the seismic data, NumPy to handle the data, Python for the overall, and importantly SciPython for all the data analysis, and Matplotlib for plotting the data. And my results were really interesting. I found that in the cities of my study, seismic vibrations decreased during the COVID-19 lockdowns from 12 to 55%. These changes happened simultaneously in all cities right when the lockdowns were enforced. Furthermore, the decrease in seismic vibrations was by over 50% in some of the cities, like Montreal and Calgary. Another interesting result was that I found that seismic vibrations were actually lower on the weekends compared to weekdays. And this is because during the lockdowns, activities that usually happen on weekends, like going to the mall in the evening or going to bars or shopping, didn't happen during the COVID-19 lockdown. So it made sense that seismic vibrations were that much lower during the lockdown on weekends than on weekdays. And this decrease was by over 50%. From my results, I was able to get 4 main conclusions. First, anthropogenic seismic vibrations did decrease during the COVID-19 lockdown. Furthermore, the decrease was simultaneous, as shown in the table, where lighter areas represent places with higher seismic vibrations and darker areas represent time with lower levels of seismic vibrations. And it's clear that there's a seismic silence between the lockdown period from mid-March to mid-May 2020. Furthermore, the seismic vibration can serve as a proxy for measuring the changes in human activities. Because I compared the reduction in human activities that I measured from mobility trend data by the Apple company, and the decrease that Apple measured in the movement of their devices matched with the decrease in seismic vibrations that I measured for Canadian cities. Third, these seismic vibrations can in turn be used to understand what is the possible sources of human activities during the lockdown. Because since seismic vibrations were lower on weekends, people can see that if seismic vibrations were to go higher on weekends, then activities like malls are still happening. So that allows you to understand what is actually causing this human activities. Finally, the decrease in Canada that I measured of 12 to 55% matched with the decrease in seismic vibrations in cities around the world done by a global study of over 77 countries, which measured a dip in up to 50% in cities around the world, which matched very well with my results. Now, to bring science to policymakers and allow anyone in the world to understand the effect of their lockdowns. And allow policymakers to make evidence-based decision-making during the lockdown, I turned my results into a web app, monitormylockdown.com. Now I'm going to give you a short demo of my website. So what my website allows you to understand is 3 things. So first, you can choose the city of the study. So right now, I'm going to choose Ottawa, which is the capital of Canada. The first thing it tells you is what is the current level of seismic vibrations. So right now, in the past month, it shows that seismic vibrations have been 6% lower in the past month. And this makes sense because recently COVID-19 cases have been decreasing in Canada, including in Ottawa. So lockdown restrictions have rapidly been lifted recently. So it makes sense that seismic vibrations are around the same as they were before. But it also tells you the level of decrease during the first lockdown. So it shows that during the first lockdown, the decrease in human activity was by over 57%. Third, my web app also allows policymakers to understand the changes between weekends and weekdays. So here, for example, you can choose the past month, and you can see that on weekdays, seismic vibrations in the level is by over 6, while weekends are half as that, So it allows you to see that on weekends, seismic vibrations have been about 50% as what they were on weekdays for Ottawa in that time period. So finally, it also allows you to understand the sources of human vibrations. So you can see the decrease in seismic vibration that happen in different frequencies, because even if human activity is normally get in the 5 to 20 hertz range, you can also look at the change in different frequencies. Like car traffic usually happens within the 15 to 25 hertz frequency. So if I were to compare the decrease in 10 to 15 hertz, which is only by 25% decrease, and then look at the decrease in the 15 to 20 hertz band, the decrease in the 15 to 20 hertz band is almost double of the decrease in the previous band. And this is because traffic, which was most affected during the lockdowns, mostly happens within the 15 to 20 hertz band. So basically what policymakers can do using this data is enforce surgical lockdowns based on time and location. Policymakers can see and predict where COVID-19 cases are likely to happen and enforce surgical lockdowns in those areas. Also, health workers can use the tool to predict spikes in COVID-19 cases and open pop-up vaccination clinics and move testing kits to those areas to better handle the COVID-19 pandemic. I've been expanding my project to other countries in the world which were facing rising number of COVID-19 cases. This includes Madrid, Spain, Argentina, Brazil, and Poland. And the decrease in seismic vibrations I measured in these cities and other countries matched the decrease that I measured for Canadian cities. So you can see, for example, in Madrid, Spain, the decrease is by almost 50% during lockdown. I even, in fact, updated my app to include those areas as well. So here, for example, you can see there's other locations in the globe. So I can pick Santiago here, and I'll also be able to get information on the levels of decrease during the lockdown. I've taken my code and made an open source tutorial and a training module on GitHub. And it walks you through the steps in around 3 hours to replicate the same results that I did for any city around the world. And this is great because now anyone can use my tool to measure the reduction in human activity in any city around the world. Since it's pandemic times, we are only safe when everyone is safe. To reach the word and allow more people to know about my project, I've been presenting my project at several different places, and I've even met several policymakers. For example, I met up in a 30-minute interview with the Minister of Natural Resources in Canada to discuss about how my project can be used in future pandemics, as well as investments in urban seismology, which means seeding big cities in Canada with more seismic stations to get a better idea of where exactly in the city are lockdowns working and where they're not. Since this decade, from 2021 to 2030, has been declared as the United Nations Decade of Ocean Science for Sustainable Development, I've been expanding the knowledge from my project into oceans. Because in the oceans, there was also a measured decrease in shipping traffic during lockdown. So I am planning to apply the same knowledge that I used in this project to understand ocean health and marine biodiversity. Thank you. I'd be happy to go over any part of my code or answer any questions. Thank you.
Thank you, Artosh. That was a very impressive talk. Very cool. All right, we have a couple of questions here. Let's start here. Let's see. Show on stage. Let's start with this question. What's a simple example or comparison to help us quantify the magnitude of the vibrations? Or is it easier to compare bigger to smaller cities?
Yeah, that's a great question. Well, in fact, yes, seismic vibration levels would be different in smaller cities and bigger cities, because in bigger cities, obviously, there's much higher levels of traffic and human activity. But in my project specifically, since I was looking to measure the really change in seismic vibrations, so what I did for all those cities is measure the average level of seismic vibrations that happened before the lockdown and the average level during the lockdown, and then calculate the percentage decrease between those two numbers. So this meant that my measurements were uniform across all cities. So I didn't actually have to quantify for the levels of seismic vibrations in higher or lower cities because I was specifically looking at the change.
Okay, that makes sense. All right, how about this? What tools did you use in making the web app?
Well, the web app was in fact made in Python, so it was coded natively in Python using tools like Bokeh, and yeah, it's hosted on a server, and yeah.
All right, great. And do you have any idea why some cities decreased more than others? Did you dig in that direction?
Absolutely. So there's several reasons in which some size cities decrease less than the others. So first, the obvious reason would be that lockdown restrictions are different. And as shown in my previous diagrams, the decrease was much more for bigger cities, which made sense. Like in Montreal and Ottawa, Montreal and Calgary, the decrease was by over 50%, while in some smaller cities, it was only by about 20%. And this is obviously because bigger cities were facing larger numbers of COVID-19 cases, so that lockdowns were much more stringent. But another main reason behind this is that the lockdowns in force were also at different levels. Some cities experienced lockdowns at the provincial level. Some lockdowns were followed at the federal level. Some lockdowns were declared by public health agencies. Some lockdowns counted schools as essential, some counted schools as non essential. So the levels of change of how the lockdowns were enforced were definitely had an impact on these changes.
Okay, that makes sense. Okay, and let me see. Did you look at, you showed for North America and as well as some South America, did you look into the Indian Peninsula at all or anything you can show from other parts of the world at the moment by any chance?
So the start of my project was to Canada, but I do plan on expanding it to countries all around the world, including in the Indian Peninsula. So I've been working on that, and in the future, this would be available for countries around the world. And obviously, through the GitHub tutorial, anyone who wishes to could also replicate the results for India.
All right. What sorts of changes can policymakers enact with your data? And maybe along with that question, you could, if there was anything that it was interesting that came up in those conversations you had with the policymakers, that'd be interesting to hear too.
Sure. So the main use that policymakers can do using my web app and data is better manage the COVID-19 pandemic. So it gives them evidence to make their decisions on. So, for example, in Ontario, I've been given the change in seismic vibrations for several cities, including Toronto and Ottawa. Now, usually the lockdowns have been very blanket-wise. So Ontario, for example, has gone when it went into lockdown, it went to a full lockdown, not taking into the circumstances of individual cities. So even though, for example, cases were happening mainly in Toronto and surrounding big cities around Toronto, the lockdown was enforced across the whole province. So using my web app, though, policymakers can really understand where exactly in Toronto or the Greater Toronto area are seismic vibrations not going down during the lockdown. And they can understand that these are the areas of the province or these are the areas of the city where lockdowns are not enforced. Or even these are the times during the day where the lockdown restrictions are not being followed. So they can use that information to better enforce lockdowns. For example, if they see that the public transportation of caused vibrations has been decreasing, but for example, construction activity has not been decreasing, instead of increasing the lockdown on both of these things, they can specifically increase the lockdown measures on construction, which would decrease the overall impact of the COVID-19 lockdowns on our society.
Now, I think, could you get the high resolution data? Like, does data exist to be able to like dig down into a city that far to say like this part, say for a big city, this part of the city is more quiet now relatively versus this part of the city? Does that level of data exist?
Well, how that would be done is you need a handful of seismic stations in that city, and you can use network analysis to understand where in the city are seismic vibrations lower and higher. Though right now, seismic vibrations have not been placed multiple in several cities. So in some cities, while there are more seismic vibrations, and that's why I've been talking to policymakers to talk about investment in urban seismology, which is seeding seismic stations into bigger cities. So you can have a handful of, for example, 10 seismic stations in Toronto, which are placed in public areas like libraries. And this will allow for a much more higher resolution of data, though for now, my study has been limited to one seismic station per city.
Do you know, just by chance, if they're very expensive? Like, is that a very cost-effective way to kind of passively monitor people?
Now, that's a really great question because the current seismic stations are usually used to measure earthquake events. So those are much bigger seismic stations that are placed much deeper under the ground. So obviously they're slightly more expensive to place. But in the case of urban seismology, we don't really need such complex seismic stations. We only need much smaller units. And in fact, seismic stations so mobile seismic stations have really been on the rise. So there's something called Raspberry Shake, in which you can purchase, for example, a pretty accurate seismic station for just a few $100s. And this can be placed easily in anywhere that has an internet connection. So with these new, smaller mobile seismic stations on the rise, all it would take is a few $1,000s to see a city with seismic stations.
Wow. Okay, now I hope that this doesn't call you out too much, but it looked like on your web app, like you are a year 9 student. So you're in high school?
Yeah, I'm going to grade 10 next year.
Going into grade 10. That is incredibly impressive. I mean, this was good work for anybody. And to see this coming out of high school student, that's incredible. Would you mind talking about how you got into the project or how you got into Python and how you ended up at SciPy or any sort of things like this, roadblocks you faced or advice you'd want to pass on?
Sure. Oh, well, I got into coding, space, and geoscience a long time ago. So it started probably 6, 7 years ago when I attended my first hackathon. So it was a NASA Space Apps in Toronto. And that really encouraged me to keep going to new hackathons. So I think to date I've attended over 50 or 60 hackathons
Well,
in my life. So to learn Python, it was mostly on my own, really, because I believe that the best way to learn is by doing. So that's why I've made so many such projects. And I also believe that the best way of learning is by teaching others, which is why I give workshops and presentations to students in schools and maker festivals. Um, for this project specifically, though, it started after my school turned online. Because once my school turned online, I had so much more time to pursue stuff of my interests, and I was really curious about what were the changes that were happening in my environment during this lockdown. Because life had become so different, and after that, I attended a small hackathon. By Seismic Underground, which is a seismic community, and I knew nothing about seismic vibrations. But after attending that hackathon, that it got me thinking, hey, why don't I mix my knowledge, my newly gained knowledge in seismic vibrations, with my knowledge on big data and COVID-19? And that's how this project started.
wow. And how did you end up at SciPy?
Well, I actually presented at the last SciPy conferences.
Oh, you did?
Conference as well. Like the T-shirt.
Are you wearing it even? Ah, nice.
Yeah. Yeah, and SciPy is definitely a library I use all the time, whether it's for some machine learning algorithms or for handling big data. So SciPy conference was definitely a place of interest.
Wow. Would you have advice for other people who, I mean, you said you've been actively talking to people and giving advice. Do you have anything you'd want to say here to pass on?
Yeah, sure. So I'd say that it's really important if you want to start doing something to find something you're really interested in, whether it be big data and or solving something. Basically, be passionate about a problem in your society, and then you have to persevere to make that happen. So the best way, obviously, is by making projects because learning is not enough. You actually need to put your learnings into application. So I've always learned that even doing one simple project I learned so much more skills than taking one whole online course. So doing is definitely the best way of starting.
That's great advice. Okay, awesome. Okay, another question here. What units were the vibrational intensity in?
Right. So for the units, so usually you would measure it, but for my project, again, I only wanted to measure the change in seismic vibrations. So what I did is I measured the power spectral densities in my data to get my results. So the units that were my data was really in was power. Which is the term, but since I've been normalizing all my data, there isn't really a proper unit that represents the data because it's all normalized.
Okay, yeah, fair enough. All right, and another question, what do you think, Do you think you'll continue more down this direction? Like you've mentioned a few directions you can go. Do you think you'll pursue that, or do you plan to expand to a different project going forward?
Well, this project definitely has room for expansion, but I'm definitely also looking to pursue other problems because there's so many new things to try out. And since I'm still in high school, I'm going to keep pursuing other projects as well, so I can keep learning and solving other bigger problems.
Okay. All right. Sounds great. I think, we've gotten time for so many questions. I think this is a good place to stop. I really hope you'll stay involved with the SciPy community. We're looking forward to seeing what you do next.
For sure. Thank you.
Thanks.